Welcome back, everyone. Hope you're all staying warm and safe. It's sure nice to be back in my house. This was a little bit exciting at times, but we made it through. And it looks like things are going to continue to get warmer over the weekend. I have to think that by next week, the weather will kind of come back to normal. So one thing that I told the others was if we had to have, if we had to pick a couple of chapters to do non-contemporaneously, in other words, where we don't really have a class like this, amines would have been one of them, just because it's a relatively short chapter. And this one even more so. This chapter is even shorter, the one on nucleic acids. So let me explain a little bit about my goals, my philosophy when it comes to these biochem chapters. There are about half a dozen of them on the various different types of biomolecules. And also there's a chapter on metabolism that will act almost as kind of a capstone to the entire year of organic chemistry. And it's been a long time. It's been over 15 years. You know, most of my career, they've included biochem chapters in organic chemistry textbooks. And to my kind of astonishment and dismay, they always write these chapters so that, you know, 2/3 to 3/4 of them is material that you got in probably high school biology, certainly in freshman bio. And those are exactly the things that I'm not going to focus on, because you will get that content in your biology classes. And many of you going on to biochemistry, which I understand is not all of you, but if I had to guess, it's probably 70 to 75% of you at least will go on to biochemistry. And there you'll cover that same type of material in more detail. I do not consider myself qualified to teach about biological function. That's not my background. That's not what my education is in. And in any case, I think it would be kind of an insult to you guys if I tried. I think most of you know a heck of a lot more than I do about those things from the classes you've taken recently. And whereas I had maybe like one such class, I don't know, 30, 35 years ago, it just would not make any sense for me to try to teach that sort of thing. And again, I don't really believe it's appropriate for an organic chemistry class. So I want to be very clear. I'm not putting down the topics having to do with biological function at all. I have no gripe against them. I just don't think they belong in an organic chemistry class. So in the class notes, this one being no exception, of the biochemistry chapters, I'm always very clear, I think, in which sections of the chapter you're not going to be responsible for. And I think you'll find it's quite often in over 50% of it. Instead, what I'm going to focus on when we cover these biochem chapters is those same topics, the topics involving those biomolecules from the perspective of an organic chemist. And I've already received feedback from past students, not just here, but also at my previous school, that this type of treatment is very helpful background for those going on to biochemistry, because the topics we'll cover with these biomolecules are exactly not the things that they're going to talk about pretty much at all. They'll very rapidly gloss over the things we cover in this class, which are structure. I think by now you've figured out that we organic chemists are rather obsessed with structure. Certainly mechanism where possible and appropriate. Certainly reactivity or chemical function. That's another main feature of an organic chemistry class, is learning about the reactivity of organic molecules. And what we'll find, I think in all cases, is the reactivity is pretty much something we already know about, having already covered various different functional groups. So that's why I kind of spread out the biochem chapters throughout the term. I always try to put any given chapter pretty close to where we discuss the main functional group there. Yeah, I've tried my best. It's not perfect, but I've tried. So for example, we've just talked about amines. Well, all that the nitrogen bases in nucleic acids are would be nitrogen-containing heterocycles. And indeed, that's the reason we call them the nitrogen bases. It's because they really are bases, like ammonia. They really are alkaline molecules. I remember, I was probably being a little bit cocky at the time, but I remember asking my biology professor in my freshman year why they're called bases. You know, this sort of swagger. You know, I'm a chemistry major. I was young and stupid. Anyway, but she sort of chuckled at me and said, yes, they really are bases. Like they have the ability to accept a proton or donate an electron. I'm sorry, yeah, accept a proton or donate an electron pair, like ammonia. And that's very true. And that's the sort of tidbit, that sort of reference to structure that I think is going to be very helpful when you get to biochemistry. I realize you're not all going on to biochemistry. I understand we have engineering majors and material science type coursework going on there. That being said, I don't think it's going to do you any harm to learn something about the structure of the molecules of life as we understand it. We're not really going to go much beyond, if any, or if at all, what we cover in traditional organic chemistry chapters. And that's another reason I like to spread the biochem chapters out, because they have a completely different format than the traditional organic chemistry chapters. And so as a result, if we kept them all together, I'd be afraid that one exam would just be so wildly different from all of the others. I don't even want to try doing it that way. So what I'm doing here at A&M is what I've always done at my previous school also. And again, and not to toot my own horn, but the feedback I've gotten both here and at my previous school is pretty good. Students have confirmed that it's exactly like I've said, that the things we will cover about nucleic acids or amino acids or carbohydrates, etc., lipids, that the things we cover here are exactly not what your biochem professors will emphasize, and also that it's very good background. And I think we'll see that all of these biomolecules, though, you know, they're large and they're complicated, yet we can understand them based already on our background in terms of how they're put together from smaller parts. And so that's what we're going to do here. So basically, what I want to cover is, first of all, some information on these nitrogen bases themselves. Another thing I want to cover that I'm not entirely happy about how clear your book makes this, and your book is not unusual. In fact, your book is probably less bad than a bunch of others I've used. I feel like I've taught from pretty much every major author's textbook. And what I mean is, I don't like, they don't clarify to my satisfaction the difference between nucleosides and nucleotides. So that's going to be something I'm going to hit upon very heavily. And then if we can get to the point where we can draw small oligonucleotides, 2, 3, maybe 4 bases, I think that will be good. That will be useful background to you going forward, that you understand how these things are put together. And if we can do that much, I'm pretty happy. And last time we ended at least 5 minutes early. It'll probably be even more so now because I've already drawn all the structures I can draw. So I think, so I wanted to spend all the time drawing the structures. Anyway, that's kind of my plan for this chapter. Just a reminder, the material we're doing today will not be on your first exam, right? It's going to be in exam number 2. The same for the material in the video I uploaded Wednesday night, which was what I would have covered had we had class on Wednesday. Likewise, we aren't really officially having class today either. I assume we'll be officially having class starting Monday, If not, then I'm just going to do the same thing again, by the way. I'm just going to show up at the normal class time and for my office hours, and whosoever will may come, that type of thing. Now, on Monday, we covered, or rather, we didn't cover, right? I uploaded that one non-contemporaneously to YouTube also. That was on carbon-13 NMR. That is fair game for your first exam. So the one thing in chapter 13 that is not fair game for the first exam is proton NMR. We haven't covered that yet, and we won't cover that until much later. That will wind up being on exam number 4, if you're curious. And again, I'm hoping you guys will trust me. I think I have good reason for doing that. That when we finally get to proton NMR, I think you'll see there's a method to my madness. So that being said, please refer to the syllabus. It's very clear about what will and will not be on the exam. And that's not going to change. The coverage will be exactly the same as if we'd had the exam well today. So other than that, not to be rude, but I think I'll mute everyone. And of course, as usual, you guys can just watch. If you have a question you want to type at me in chat, that's completely fine. Actually, we might need to get an F in chat for all of the power outages all over the state, right? I think it deserves at least that much. Wait. So there we go. I'll get that started. Good. So we've already, in all seriousness, we've already covered about the nitrogen bases, and these are they that we find in DNA and RNA. If this were an ordinary semester, I would be saying you do not have to memorize all these structures, and you still don't. And actually, it doesn't even matter because if you need them, you can look them up. So, but I am not interested in making students memorize all these structures. That's just not who I am. Now, if you go on to biochemistry, you might get that pleasure of having to memorize all of these molecules. But I would like to give some background on them so that you understand more about their structure. And I think, again, I think it will be good background for you going forward. So you might have heard that adenine and guanine are called the purines, and cytosine, thymine, and uracil are your pyrimidines. Thymine and uracil, of course, differ in a methyl group. I'm sure you were told that even in high school biology. And of course, the one without the methyl group, uracil, we find only in RNA, and the one with the methyl group, thymine, we find only in DNA. That's not that you couldn't draw structures that have that backwards, but those would not be naturally occurring compounds, right? They would be unnatural compounds. So the reason adenine and guanine are called purines is because there is actually a compound called purine, and this is it. It's an aromatic heterocycle with 2 fused rings, 5 and 6 membered fused rings, and 4 nitrogens. Purine is a 10 pi system, so 2, 4, 6, 8, and actually the lone pair on this nitrogen makes 10 electrons. So these 2 electrons are included in the pi system. The other lone pairs on nitrogen are not. Those, I would encourage you to draw that out. Just like we did in chapter 15. And I think you'll be able to convince yourselves that those 3 lone pairs are in sp2 hybrid orbitals that stick out from the ring. They're not included in the pi system. And likewise, the reason we call these things pyrimidines is because they look like pyrimidine. They have a similar structure to pyrimidine. They're in different isomeric forms, which we'll get to in just a moment. Pyrimidine also is an aromatic heterocycle. It's kind of like pyridine. Of course, pyridine just has 1 benzene CH replaced by a nitrogen. Pyrimidine is 2, and they're sort of 1-3 relative to each other. And again, I think you'll find that this is a 6 pi system. Those 2 lone pairs are not included in the pi system. They're not pi electrons. They're in the sp2 hybrid orbitals, but 2, 4, 6, just like benzene. So, the way I remember which are the purines and the pyrimidines, you may think this is kind of stupid. You might find it helpful. You might think both. You might think it's both stupid and helpful. Whatever. I'm fine with any or all of the above. the way I remember which are purines and which are pyrimidines is purine is the smaller word, but the larger heterocycle. And pyrimidine is the larger word that goes with the smaller heterocycle. So the size of the heterocycles and the size of the words do not go together. Purines are the larger heterocycle, pyrimidines the smaller heterocycle. So, and like I said, if you should need these on exam number 2, you can just look them up. But I would never be interested in people memorizing that sort of thing. So the next thing I want to point out, you might have kind of been looking askance, let's say, at the structure of guanine, or really the structure of any of these pyrimidines. It's sort of like we've ruined the aromaticity. And so you're thinking, well, why are they in that form? We've made the ring non-aromatic now. And it's a very good question, and there's also a very good answer for it. Here I'm using, let me see, I think that's cytosine. So I'm just using cytosine as an example. This gets into something known as keto and enol forms, which I'm almost positive those words escaped my mouth once or twice last term. It's not something we'll get into in detail until round and about maybe chapter 19, or I don't know if we'll find it in 16, but we'll get to that when we start getting to carbonyl chemistry, which, by the way, is coming up next. So, and it's going to be a major part of the course. Carbonyl chemistry is always a goodly percentage, traditionally, of any organic chemistry 2 courses. Probably 60–65%, if not even a little more, of the material is on carbonyl chemistry. So this is the form that we find cytosine in when we actually look at the structure of natural nucleic acids. And again, this is not aromatic. We call this the keto form because we've got a carbonyl group in it. We've got C double bond O. The other isomer that we would get would look like this, and that we call the enol form. And they would call it that because that's exactly what it is, enol, right? It's a carbon-carbon double bond and an OH group. So we call that the enol form. And there's, in general, there's a few exceptions due to having, particularly limited cases with structures. But I think you'll find 95+% of any carbonyl compound, not just ketones and aldehydes, but any carbonyl compound, most of them will have both a keto form and an enol form. In this case, the enol form looks like it should predominate because you've now got an aromatic ring again. And I do want to point out we need to be very, very clear on this. Please remember, this is not a resonance situation. You'll notice I've drawn an equilibrium arrow here. So these two are not resonance contributors to each other. And the way you know that is because atoms have moved. This H was on the nitrogen, now it's in the oxygen. You're not allowed to move atoms in a resonance situation, right? You're only allowed to consider different placement of electrons. So this really is an equilibrium. These are going back and forth rapidly in aqueous solution. And again, if I were just to guess, I would have guessed the enol form would predominate. But it turns out that it's the keto form that predominates. And that for a couple of reasons. First of all, in these pyrimidines, you'll notice it's this hydrogen on the nitrogen, it's this nitrogen-hydrogen bond. That's the one that we're going to replace with a nitrogen carbon bond when we make the so-called NO acetal, which we'll define shortly, and we make the nucleoside. And the other reason is, both for pyrimidines and for purines, as I pointed out over here, it turns out these keto forms are better at hydrogen bonding than the enol form. They're better hydrogen bond acceptors. We don't have that. We don't quite have those options in the enol form. So those are the reasons. And again, that's the sort of thing with the emphasis we have on structure that I feel I can really bring to this material. Because otherwise, anyone who looked at those two structures with an open mind and some organic chemistry background, why is it not this? Well, those are the two reasons. First of all, because we need that NH bond to form nucleosides, which we're getting to next. And second of all, because otherwise we wouldn't be able to do the hydrogen bonding. And I think you all know about the importance of hydrogen bonding, how the two strands of either DNA or RNA are held together by hydrogen bonds. These are the sort of things that I really feel that these sorts of things should be common knowledge, at least among those who have a college degree, anything remotely close to science. So that's sort of the, if you want to know what the principle I use is for the things I mention and do not mention when we cover biochemical topics, the things that I mention really are going to be the things that even I know. And I am not a biologist. And as I've said, I'm 30 plus years away from biology class. But there are things that even I know. And so those things I will feel free to mention, because I'm pretty confident you guys know them too. Okay, so as I said, I wanted to get very clear on what is a nucleoside and what is a nucleotide. It's the sort of thing, again, that I bet you'll find when you get to biochemistry. They just start throwing around those words. But I would like us to be very clear about the difference between a nucleoside and a nucleotide. And so we'll draw some examples, of course. But I've defined nucleoside here. It's what we call an NO-acetal, and I'll explain and define that term a little more clearly in a moment. By the way, acetals are something we're going to get to in chapter 16. So this is just a special kind of acetal. We'll learn about a functional group known as an acetal. Basically, acetals are species that involve an sp3 hybridized carbon sitting between two oxygens. So there's two carbon-oxygen single bonds. We call those guys acetals in certain circumstances. And the only difference here, the reason we call this an NO-acetal is because instead of the carbon being between two oxygens, it's between a nitrogen and an oxygen. That's the only difference, though. So, so in a typical nucleoside, here I've taken, I think that's adenine. Just don't want to lie to you. Yep, that's adenine. And there I go flexing again. I just so you know, I was able to draw that adenine with one mouse click. They're in my template section here. So I was surprised I couldn't find the ribose. It probably is in there somewhere, but I had to draw the ribose out by hand. Let me just go back to you don't have to concern yourself with that 3D business if you don't really want to. So that's also fun, but I'll get to that later. So this is an example of a nucleoside. And what I've done is taken one of the nitrogen bases over here. We've taken an adenine, and we've used nitrogen 9. It's always going to be this nitrogen in the 5-membered ring of the pyrimidine, of the purines. Whereas in the pyrimidines, it's nitrogen 1. It's one of these nitrogens down here, kind of yonder across from the NH2 group in cytosine and from these carbonyls in thymine or uracil. So those are the nitrogens that get used to make that NO-acetal. And what else do I need to say about that? And what do we make an NO-acetal to? Well, this here is ribose or deoxyribose. So that's a sugar molecule. This type of drawing of a sugar is known as a Haworth projection, in case you're curious, Haworth. We'll get to those when we talk about carbohydrates, but it's a very common way of drawing pentoses and hexoses, so 5 and 6 carbon sugars. There's good and there's bad about it. The really good thing about Haworth projections is it becomes really, really clear whether a group is pointing up or down on that sugar ring. The bad part is, as you can see, we kind of throw bond angles out the window, right? You got some apparently 180-degree bond angles. So that's the weakness. But it depends what you're trying to show. And if you're interested in emphasizing, as biologists and biochemists often very reasonably are, well, then Haworth projections are just perfect for that. So there's our NO-acetal. You can see the acetal carbon is right there. It's sitting between the oxygen and the nitrogen. The nitrogen is the one that was in the nitrogen base ring, and the oxygen was already there in the ribose or deoxyribose. I here put R because that R is going to determine whether this adenine is involved in, here I'm just using adenine as an example, I could have picked any of the others, but that's what's going to determine whether this nucleoside is of the type you'd find in DNA or the type you'd find in RNA. And again, I feel you've almost certainly been told this in past classes. That's where we get the name DNA for deoxyribonucleic acid. So we need to deoxygenate it, and we'll change the OH that we'd normally find in ribose here on the so-called 2' carbon, more on that in a second. We change that OH to a hydrogen. And so if this were an adenine that you would find, or an adenine nucleoside that you'd find in DNA, this would be a hydrogen. If in RNA, that would be OH. And indeed, the normal sugar by itself, ribose will have OH over here. And instead of this nitrogen, it will also have another OH pointing up over here. That's ribose just by itself. So effectively, to form these nucleosides, we have to condense our nitrogen base together with the ribose or deoxyribose. We'll learn how that's done, by the way, in chapter 16. We'll learn the mechanism then. But the mechanism is going to be the same for this, and it goes with losing a molecule of water. So I would call that a condensation reaction, since we're losing a small molecule and bringing two big molecules together. And in this case, the small molecule we lose is water. So this is another thing you might have wondered about, and something that I bet is your biochem professor will gloss over. And again, I don't mean to put down your future biochem professor. They have a very different focus when they cover their material, as they should. You know, they're covering what they need to cover. But I would like you to know why you're all of a sudden seeing 2', 3', and 5'. What are all these primes? What are they for? Where did they come from? Why do we say that the DNA type of nucleoside is deoxygenated at the 2' carbon? Well, the reason we put primes on the numbers for the atoms in the sugar is because we need to distinguish them from the numbering of the atoms in the nitrogen heterocycle. It turns out that it's atom 9, nitrogen 9 over here, that's going to attach to the sugar with a purine. And as I said, it's nitrogen 1, which I pointed out which one that was. That will attach for pyrimidines. And by the way, I happen to know that's nitrogen 9. If you were going to ask me which one is atom 1, I couldn't tell you. I'll just let you know that numbering atoms on heterocycles is bizarre. That stuff was figured out at least 80 or 100 years ago. And if you want to look up where that numbering came from, you can go look up in dusty old books. You'll probably have to look in the original Beilstein series, and I hope your German is good, because they're in German. So good luck with that. But that's already been long ago decided, before any of us came along, and seems sometimes kind of arbitrary. But numbering of atoms in heterocycles is weird, but it, for better or worse, was settled a long time ago. So that's why we put primes on these when we're talking about nucleosides, because we want to be sure we're clear as to whether we're numbering the atoms in the sugar or the atoms in the heterocycle. So that's why we call this the 5' carbon in the context of a nucleoside or nucleotide. We just want to be clear that we're numbering these 1, 2, 3, 4, 5. That numbering system at least makes sense. Carbon 1 is going to be the acetal carbon, always. And we'll learn why that is in when we get to the chapter in carbohydrates. And then we just go around 2, 3, 4, 5. And so ribose and deoxyribose are both 5 carbon sugars. So that's basically how nucleosides are put together. And yeah, it's a large molecule, but I think when we take the time to go over the structure like that and describe it, I don't think there's anything here that's overwhelming. There's nothing here that we can't understand. based on previous content that we've had. And yeah, we'll have more to say about acetals in particular when we get to chapter 16 coming up next week. But other than that, I don't think there's anything here that's out of your reach. So much for nucleosides then. As I said, I wanted to be very clear on the difference between a nucleoside and a nucleotide. That's one of the main things that I'd like you guys to get out of this chapter, because again, I'm not confident that if you have biochemistry in the future, that they'll make very much of that. And it's something I remember finding confusing until I sat down and looked at it carefully because I had to teach on it. So let's make that clarification over here. Here I've taken the same adenine nucleotide, and this could be either DNA or RNA type. I'm sorry, nucleoside. And in order to go from a nucleoside to a nucleotide, all we need to do is attach either a phosphate, a diphosphate, or a triphosphate ester to either the 5' hydrogen over here, or the 5' oxygen, I should say, or the 3' oxygen. There's your OH over here. Either way, so you can have either one phosphate, this is a diphosphate. If we had a triphosphate, we'd just add one more phosphorus. If we put that either on the 5' oxygen or on the 3' oxygen, then you've got yourself a nucleotide, not a nucleoside. And just so you see what I mean, let me just show you how that would look like with just one. Why is it not, why no delete? Let me just show you what that would look like with just one phosphate ester. I also want to dwell a little bit. There, I don't know what just happened. I also want to dwell a little bit on, just by way of reminding you about hypervalent atoms. Of course, you'll notice the phosphorus atom rather is 10 electrons around it, whether it's this would be an example of a monophosphate. And if you move that over to the 3' oxygen, that would still be a nucleotide. But remember, as for phosphorus having 10 electrons around it, remember that the atoms in the 3rd row of the periodic table and below can become hypervalent. They don't have to, but they can. Even more important than that, though, I would say, is to remember that the atoms in the 2nd row of the periodic table, so carbon, nitrogen, oxygen, these ones, can never, ever, ever become hypervalent. There are absolutely no exceptions to that. They will never, ever have more than 8 electrons around them. Now, you might have been told what I told my students pretty much my entire career at my previous school, and probably into the 1st year here, is what you might have been told, or even by your Gen Chem professor, is the reason that elements in the 3rd row and below can become hypervalent is because of d orbitals. And it sounds very plausible. Indeed, in the 3rd energy level, the 3D subshell opens for business. And even though the 3D orbitals are all empty when we're at phosphorus, right? This is a p block element, no pun intended, right? This is here we're still filling the 3p subshell, and the 3D subshell is higher in energy than that. But those orbitals are there to accept electron density. So that's what we'd always told them. Oh, you know, you can put the extra electron density into the d orbitals, and it sounds very plausible. But it turns out that more recent studies involving very high-level computations of molecules like this, involving phosphorus or sulfur or silicon, that there's almost no d orbital involvement. So now we think it has more to do with electronegativity and perhaps atomic size. So it's something a little bit more basic than that, if you will. But until then, it was a very plausible explanation. The reason why oxygen can become hypervalent, we're in the 2nd energy level, there is no 2D subshell, there's no such thing. So it makes sense, but it turns out that's probably not the right explanation. It probably is more to do with other properties of the atoms, like atomic size and electronegativity. Good, so that's an example of a nucleotide. And I've left, so that is all we really need to know to understand what we'll find in terms of, if you will, the primary structure of DNA and RNA, now that we understand what a nucleotide is. And when we want to string together multiple nucleotides to draw the structure of a small piece of a nucleic acid as you would find it in living systems, all we need to do is connect the two nucleotides with a monophosphate ester between the 3' OH of one nucleotide and the 5' OH of the next one. And that's another thing I really want to emphasize. And it's something students often get confused over. But that part is invariant. It's always a monophosphate ester between any two nucleotides. That never changes. That's invariant. And so I put a sample exam question here. Draw a dinucleotide with both of the nitrogen bases being cytosine of the type you'd find in RNA, and then put a diphosphate at the 5' end. I've already put that in your class notes. So I think you'll see that's what we've done. I've looked up those structures, or actually in my case, I have little doubt that I just drew them in one mouse click. But even though you can't do that, you will be able to just look up those structures. I do not expect you to memorize the structures of nitrogen bases. Then again, notice here's the 3' oxygen of this one, and here's the 5' oxygen of the next one. Notice that between those two oxygens, we always have a monophosphate. That never changes. There are no exceptions. There's always one phosphate there. And it's said to put a diphosphate at the 5' end. Well, there you go. If we'd left that as OH, that would have been the 5' OH. Instead, for whatever reason, the question said to put a diphosphate there. If it had said triphosphate, we'd have put a triphosphate. Monophosphate, we'd have put a monophosphate there. If instead it had said to put it at the 3' end, then we would put it over here. So this over here is your free 3' OH. But that part never changes. And you'll also notice that at the 2' carbons, that's what I mentioned before. You see how I've kind of made this look a little more 3D by making those sort of wedge bonds. You may do that if you like, and you will often find it drawn that way. But you don't have to. If you'd rather just draw it like this, that's also perfectly acceptable. You'll see Haworth productions drawn both ways. But you might prefer to put a little bit of perspective into it, make it look like it's really perpendicular to your paper. So that's up to you. You can do that either way. But be that as it may, so again, this monophosphate ester is invariant. Now you'll notice at the 2' carbons, we've got OH groups. That tells me that we've got an RNA type dinucleotide, because it's not deoxygenated. If this were a dinucleotide of the type we'd find in DNA, then we'd have H's over here, not OH's, there at the 2' carbon. And that's basically it. And so it continues. If we wanted to draw a third nucleotide, we'd make a monophosphate ester here and go to the 5' oxygen in exactly the same way of the next one, and on and on and on. That's the primary structure that you'll find in DNA and RNA. And again, yes, these are large molecules, but I think you'll agree with me that if you break them down into their parts like this, it's not hard to understand. I don't think this is beyond you guys at all, given the background that we've had in this class. And that's most of what I wanted to talk about. And I see, again, we're going to end about 5 minutes early, and that's fine. I don't think anyone's going to object. I did want to point out, as you see here, I've been very clear in the class notes which are sections that you will not be responsible for on exam number 2. So I'm always going to do that. But there's a couple other things that I think are worth us mentioning because, again, I really consider them common knowledge and should be something in the back of your mind if you're a college-educated scientist at any level. And yes, I consider doctors to be scientists. At least I hope they are. And that would include things like I said, it includes the things that even I know. You know, even I know that cytosine and guanine form base pairs, and adenine with either thymine or uracil, depending on whether you're talking about DNA or RNA, respectively. That I think is common knowledge, because I am no biochemist, and even I know that. Whether that will be on the exam, we'll have to see. I don't think I can make exactly 60 points out of that, if you know what I mean. But these are things that I consider to be common knowledge. I also pointed out here, your book goes into the full complement of material on transfer RNA and messenger RNA. And again, I'm not trying to denigrate that material at all. There's nothing wrong with it. But I think you'll agree with me, it doesn't belong in an organic chemistry class. It's not appropriate for us to cover that, if I even could, which I don't consider myself competent to do that. But there are some things I wanted to point out for the sake of future material. In one case, it does talk about, in the whole transfer RNA scheme, how it is, as you know, that we get polypeptides from nucleic acids. And polypeptides are made up of individual amino acids, which we'll go over in the chapter on amino acids and peptides. But that reaction that pops the amino acid residue off the transfer RNA and into the growing polypeptide chain, that's known as a nucleophilic acyl substitution reaction. And that's something we're going to talk about quite a bit in, I think, maybe chapter 19 or 20, 21, somewhere around in there. So we'll get to that. And that's it. What we'll learn there is the very same thing that happens in that step of putting together individual amino acids in the growing polypeptide chain. And that's going to be one of my main focuses, I'd say, going forward with this biochem material, is the things that you learn in organic chemistry are exactly the very things that we find going on in the chemistry of life as we understand it. And that's why I say our chapter on metabolism is kind of the capstone to the course for us. And then one last thing I really thought worth mentioning. This doesn't even really involve either chemistry or biology. It's really just a little bit of math, and it's not very high level math. But this whole business of the triplet codons, I'm sure you've heard that term. I'm sure you all could speak far more lengthily and competently on triplet codons than I could. But even I know, again, so to speak, that that the codons that code for individual amino acids are made up of sets of 3 nucleotides. And you might have wondered why that is. Well, the reason is because we need at least 20 different codes, because there's 20 different amino acids, as you'll find when we get to the chapter on amino acids. And by the way, I'll spoil that for you guys. Just like in this chapter, for us, you will not have to memorize all 20 amino acids. And even if the exams were a closed book, you would not have to do that. In biochemistry, you probably will have that pleasure, those of you that go on to biochemistry. For my class, no way. I'm not going to be interested in you memorizing all those. And if you should need one of them on the exam, of course, you could just look it up. But I do not want you guys spending 1 second for this class memorizing things like this. Anyway, there's 20 different amino acids. Well, that means we can't do it with just 1 nucleotide. That gives us 4 possibilities. So that's not enough. What about 2 nucleotides, groups of 2? Well, that's better. Then you get up to 16 possibilities. It's 4 squared. So it's better, we're closer, but still not enough. So that's why we need 3. That's why we need groups of 3 nucleic acids, nucleotides, in our triplet codons. Then the number of possible codes you get is 4 to the 3rd power, which is 64. And now we're good. Now we have more than enough for all the different 20 amino acid residues, plus a stop codon, plus other things like that. And of course, since we've got so many more than 20, that means that the translation code is redundant, which simply means that for many, maybe even most of the amino acids, there's multiple different codes that code for the same amino acid. However, the code for translation is not ambiguous. And I thought this was worth mentioning. I bet that's something that your biochem professor will point out, that the code for translation is redundant but not ambiguous. I just wanted to show you that that phrase there makes perfect sense. It's redundant in that any given amino acid probably has multiple possible codes for it, but it's not ambiguous because any one triplet codon, any one set of 3 nucleotides will always code for just one amino acid, or possibly the stop codon or something like that. So it's not ambiguous, but it is redundant. And honestly, if we can get that much out of this chapter, I'm happy. That really, I think, is enough for us to cover in an organic chemistry class. So with that, as I said, I don't really have anything else. If there are any questions, I'm happy to entertain them. Otherwise, my plan is on Monday, we'll do this again regardless, whether or not they say class is canceled. Of course, we won't do reef polling. I won't take attendance, not until Friday a week from today. That would be the earliest that I would take attendance, because as you saw in those emails, we can't have anything due that's graded before then.